our first talk, I welcome Gerrit and Ahmed to talk about injection molding and how AI can help us to produce less many defective parts. And without further ado, I welcome you on stage. Small round of applause for our first speakers. Come on.
All right, so welcome also from my side. Thank you for the introduction. So we'll be looking at the talk on automated process monitoring, injection molding via representation learning and setpoint regression. And to dive in, I will open the problem statement, the business context for what it is we're actually solving for our customers. Then Ahmed and Peng will focus on the methodology and also the results. And then I will close the talk with a little bit of insight on the practical implementations. All right, so let's look at the business context. Injection molding is very, very briefly a process where we have molten plastic, which is injected into a cooler mold. Heat is transferred from the molten plastic to the cooler mold, and the phase changes, and the solid part ultimately is ejected. And good news is our sensor technology from Kistler's side enables us to monitor the cavity pressure inside the mold, which is the quantity that can fingerprint the process and encodes a lot of information on it. The bad news is, however, that deciphering what is a good distribution of pressure over time and a bad distribution of pressure over time is currently subject to expert understanding. So experts have to go ahead, and if you look at this side of the PowerPoint here, experts have to define certain evaluation objects that signify if a curve is a good curve or not. And if we look at the development in manufacturing industry in general, we see a decline in interest in apprenticeships for workers on shop floors of large producing facilities. And expert knowledge becomes increasingly also expensive. And this puts us in a little bit of a problem. If we need experts to perform this monitoring, but the number of experts will decline in the next decades, also with a lot of people going into retirement, we have a problem, but we also have an opening possibility for automation. And Ahmed and Peng will tell us now a little bit about how our modeling approaches aim to solve this gap.
Thank you, Gerrit. All right, so Gerrit presented or showed the need that we have, and the basic solution approach would be kind of to transition from this manual setup of the process monitoring that is shown on the left, where we acquire a signal. I will speak a bit also what exactly this is, to a more automated process, which also not only gives an indication whether or not the process is running smoothly, but also what could be a potential issue that causes a dysfunction in the system. And I will explain this figure later, but before that, I will highlight the kind of the concepts behind our solution. So first, when we started, we wanted to keep the instrumentation and the acquisition process the same as in the manual process. So we didn't want to completely disrupt the system, but rather provide an alternative solution to the functioning manual analysis. And we divided this into two main tasks for the AI. One task is binary anomaly detection. So that means that the signal that is incoming during production is analyzed and either rated as being normal or as being not normal. And then the second task, which goes beyond what is currently provided with a manual process, would also be to provide some sort of assistance in identifying the root cause causing the issue in the process. So we start here with, or we show it on the top, you see the manual process, and this has the obvious limitations, mostly related to the reliance on the human expert. So that means that here the quality of the anomaly detection in the analysis process depends on the operator, and also it's not very reproducible. And also what you also can kind of hint at is the sensitivity and specificity of the detection is very much dependent in kind of in implicit ways. And to address these issues, of course, there are a number of challenges. Namely that a priori for a given process, so that means a given part, a given mold, and a given sensor position, for example, it's not clear or not known a priori how a good curve would look like and how a bad curve would look like. Also, it's not straightforward to acquire this kind of data. Even worse, this is for the root cause analysis. It is impractical to acquire the amount of data necessary for so-called supervised learning, where essentially one would just take all the acquired data and labeled data and then put it into a supervised learning. So we had to come up with an alternative solution that overcomes this difficulty. So I mentioned already the goal is to find we call that operational bounds of the process. So that means that in which region or what kind of signal is okay and what signal is not okay, and derive this in a data-driven way. And also a way to have the sensitivity and specificity set in a more simpler way than it is done now. And for the second task, the goal here is to have some form of interpretable quantity from which then a root cause indication can be derived, or some rules that hint to certain issues. And the specific solution that we drafted, which addresses these issues, is roughly as follows. And Pong will later go into the methodological details. Here's just the conceptual overview. So first, we take the high resolution temporal signal and map it into a low dimensional space. We call that embedding. And for that, we use representation learning. So this is the first step of the anomaly detection. Then we use, once the process is established, we use a small number of reference curves. They are known to be normal or good. And then we estimate the statistical density that describes us the typical kind of distribution of normal data. And with that, we can then, by sliding a simple threshold, we can adjust the sensitivity at which we want to detect anomalies for future measurements. So for the root cause identification, this is a bit more complicated. And here, the basic idea is to acquire data from or link data to external variables that we can control, and then learn systematic effects of these variables. And the variables that we chose are like three machine parameters that can be set at the machine. It's the back pressure, the injection speed, and the mold temperature. And because we can manipulate them, we can acquire in systematic experiments, we can acquire a lot of data that then produces a data set on which the AI can learn certain very typical changes of the curves, which then in a second stage will be indicative of the root cause. So with this overview I've given, I now kind of try to explain the kind of, again, the concept based on these figures. So in the subfigure A, you see green and red curves. The green curves are curves that are considered to be normal. Red are considered to be abnormal. And the established manual setup would consist of drawing these rectangles by humans. And now we replaced the setting of the operational bounds with the data-driven operational bounds shown here in purple. So if after the embedding a data point lies inside the ellipse, it's considered good, and if it's outside, then it's considered bad or an anomaly. And the width of this ellipse can be changed with a single parameter. And then we do systematic experimentation by varying the machine parameters, and then from this we then train in a supervised manner, in this case, some, let's say, predictions of machine parameters. And when data points lies outside, depending on like more or less outside the distribution, we can derive root causes. I make an example. This would be if the first parameter would be the back pressure, and the machine analyzes a signal and it predicts a substantially lower back pressure than expected, then this might be indicative of a clogged sensor, but it would be not, for example, indicative of a failure of the heating system of the mold. So with that, I'll pass on to Pong. He's a PhD student at the Center of Artificial Intelligence at ZHAW, and he will talk about the method that we used.
Thank you very much, Helmut.
So now let's talk about the method into detail. So our method can be divided into 3 phases. The first phase is offline training phase. So in this phase, we train our model on historical 1D time series data. And this data are unlabeled, so we learn it in unsupervised way. The idea is to learn the general features for these pressure curves. Here is an example. On the top, you can see the pressures from different scenarios. And this is a latent repetition. You can see the cluster differently into different groups. So we learned good separation for this repetition. And after we learned general features, we move to the calibration process. So in the calibration process, the idea is that after the operator set up the correct machine parameters, and the production process is going to be stable. So we get the features from this normal data. So we assume that the distribution for this normal data will stay the same. So then this can be used for detect anomalies. But in real cases, because in real production, the conditions can be really dynamic, so date drift can occur. That's why we come up with the dynamic calibration, where we move the calibration window forward after the next prediction is good. In this way, so we already keep the updated distribution of the calibration data to counteract the date drift. And after the calibration process, we set up the bound. You can see we set the decision bound depend on the customer request, and then we can use to detect anomalies. For example, here this is anomaly 1, and we get the repetition which is outside of the boundary, and then of course it's detected as anomaly. So let's talk about our model. Our model is built up on the variational encoder. You can see on the top, the input is the 1D time series pressure data, and encoded into a lower dimensional representation. And from sample, we decode it back into the same dimension of the input. Additionally, we add several more neurons to represent the mapping from the 1D pressure curve to the machine parameters. And to train the model, we use 3 loss functions. The first one is reconstruction loss, which is to minimize the error between the original and the reconstructed images, the pressures. And the second one is scale divergence, which is to force our learned repetition to approximate the Gaussian distribution. And in the end, the regression loss is used to predict the machine parameters. And our model is pretty lightweight, with less parameters. Each forward pass only took several milliseconds. So here is our result for anomaly detection. We use several evaluation metrics, and from that you can see AUC is the main evaluation metric. You can see in most of cases for the dynamic calibration is performed much better than the one batch calibration. So our model can also detect drift. So this curve shows the pressure changes over time. The light colored curve means it appears later in the time sequence. So you can see that it slowly drifts upward, right? And it's also reflect in the latent repetition. It's moved to the right and down. And we also did some experiment about root cause analysis. So here you can see these are the pressure curves with different settings where only one machine parameter changes. And this green one is the base setup. It's a calibration that maybe you can't see clearly, but they all almost overlap with the green one, which is we change the molding temperature. As you can see, they're not sensitive to the mold temperature. In the middle is the latent space. As you can see, even they are pretty similar, but the right one is still detected outside of the acceptable range. On the right, we also show the representation for the machine parameters. For example, this one is a representation for the holding pressure, and the green one are the representation from the calibration data. And you can see the blue one, when we increase the holding pressure, we want the representation also deviate from the distribution of the calibrated data. It's actually deviate. However, when we increase the injecting speed, the representation for the holding pressure also deviate. This something we are still working on, this entanglement study. So in short summary, we develop a variational encoder which can get low-dimensional representation for detect anomalies and the drift, and also some level root cause analysis. And we are still working on that, testing on more scenarios for the real production data to evaluate the effectiveness of the root cause analysis. With that, I hand over to Garrett.
Thank you very much, Pang. So very impressive already what you have achieved on the modeling side of this problem. Now a few closing remarks on the topic of technology readiness level, a scale you may know from developed by NASA for evaluating the readiness of technology for use in space applications. You can also apply it to other technologies, and this readiness level addresses not just, let's say, one component of the technology, but the entire system. So in our case, it is a sensor, it is a data processing unit, data acquisition unit, a model, and then an interaction with the user. So, and then it has to be something also marketable. So it's quite a complicated step here. I will not go through everything here, but in fact we have some training here, but then we also test the device in the lab and let it be verified by an expert who is not a data scientist, doesn't care about, let's say, the data at all, but just wants to have an easy life. And then the feedbacks we have to actually incorporate in the model and also in the device itself. So you can imagine in our vision is we have some stable process. The expert only needs to press a curve, or the non-expert in this case, and then anomalies are detected automatically. So this was our lab test. And yeah, to conclude, thank you very much for your attention.
Thank you very much, Pang, Gerrit, and Ahmed. Now we have 5 minutes for questions from the audience. Is there a microphone handed over? No, right? There. Okay.
Is it on?
Yes.
Okay. Thank you for the talk. It's very interesting. You were talking about systematic experiments to train the model. How many did you do, and how many parameters did you have?
So we had per let's say design of experiment, we did something like 200 to 300, but these are repetitive, so 10 in a batch, and we had 3 parameters and typically 3 set points per parameter, sometimes more, and we did like we constantly acquire new new series of experiments. So it goes now into the low thousands, but like every experiment adds like a couple of hundred new curves, also new parts, new molds, etc.
Thank you.
Next question, please. Just hand it over then.
Thank you for your talk. So P was 500 originally, the P, the number of, and then M is the one that you're talking about. So the reduction was to M. How many M did you have in the 3? And that 3, do you preset it, or you try to optimize and find it, or it's based on the?
Yes. So this was based on domain knowledge. That the domain experts said these are like kind of the 3 main drivers that kind of have an influence on the on the curve. So that's why 3 was selected.
I see.
Kind of a ratio between like effort and effectiveness.
Okay.
Yeah.
So P being 500 was after dimension reduction, or it was the
Sorry.
original?
Maybe I misunderstood. So the input signal to the pressure curve is 500, but this is already after downsampling. So I think I don't know, this is in the over 1,000 hertz. So it would be like much higher dimensional, but then it's compressed to roughly 500 time points.
Okay.
And these then compress down to a 2-dimensional latent space plus 3 machine parameters.
Okay. Have you tried to do it automated, the number of the M? I mean, so maybe you come up with like more than what the customer is asking.
So the reason why we take 2-dimensional subspace is mainly for 2 reasons. First, because we estimate a parametric density function, and we want to be able to estimate the parameters with something like 10 examples. We can't have much higher dimensional space for now. Okay. That's one. And second is for the visualization. Also for the user experience, we wanted to be something that users could look at, and even we experience kind of how it looks essentially.
Okay. Sure. Thanks.
Next question, please. Yeah, coming. You were also waiting. Okay, you will be next.
Yes, thank you very much. It was a great talk. One question is about root analysis of failures. Have you experience with other techniques like failure trees, Markov chains, and did you compare these techniques with ML-based models? What are advantages and disadvantages?
Maybe I pass the question to you. I guess you might be
so
better.
Internally, we at Kistler tried a couple of various approaches, and let's say we don't have like a, let's say, metric overview for you like this, but we tried a few approaches, and the current one we converged to after several investigations that it's just the most promising and the most robust. So that's as deep as I can go from.
You had a question too, right? So sorry.
Hello. So the pressure curves that you are using, this is all from the machine. You are not using like simulation to enhance your data or something like that?
It's directly from the sensor, yes.
And you try, or is there a need to enhance those data with simulations? For extreme cases, for example, or things that may lead to breakage of the machine, you cannot test on the machine?
I mean, it's a chance if you let's say for speeding up, you can create some meta models to generate new synthetic data. This is one use case for simulation which we looked at. And of course, once you know, let's say, the components of the machine and can model them very well, then you can also simulate them, but we haven't looked at that yet.
Unfortunately, time is out. And I thank you for kicking off the day. In order to get some carbohydrates into your system, there's a small gift from the Data Innovation Alliance. You have now 10 minutes to change the rooms or stay here, which I very much recommend to do so. We'll talk about the building information model next, and I see you in the next talk.